Hi everyone. So recently Google released its new open vision language model called PaliGemma or PaliGemma, depending on how you prefer to pronounce it. And it's actually a very nice vision language model that you can fine-tune for your specific use case. So that's really the goal of this model actually is to be fine-tuned on the specific tasks. And so that's actually what I would like to illustrate in today's video. So in my GitHub repository called Transformers Tutorials, you can find all kinds of notebooks for all the different models available in the Transformers library by Hugging Face. And so recently I uploaded a notebook for this PaliGemma model where I fine-tune it for a downstream task, namely for converting received images into JSON. So for instance, if you have this received image, you would like to make the model learn to output a JSON containing all the item names, their quantities for example, as well as the price, and then also the total price. And so that's why I created this notebook. I'm gonna go over it cell by cell, and we're gonna run it as well, so you can actually copy it, for example, to your Google Drive, and then you can use Google Colab to run the notebook. So of course, if you want to fine-tune such a model, you will need a GPU. For this, I personally used a NVIDIA L4 GPU, so it's already selected here by default. So yeah, make sure that you are running this notebook on a GPU. Of course, there are various GPUs available on Google Colab. For instance, the T4 is more of an older generation, which has 16 gigabytes of RAM. The L4 has 24 gigabytes of RAM, and the A100 has either 40 or 80 gigabytes of RAM. For this notebook, I think 24 will definitely suffice. I haven't actually tried it yet on the T4, but I would recommend using at least 24 gigabytes of GPU RAM. So the architecture of PaliGemma is actually fairly simple. So what they did was they took a pre-trained image encoder and they took a pre-trained large language model, and they basically fit them together with a projection layer in between. And in this way, we basically have a multi-model model that can take in both an image and a text as input and then produce text as an output. So in this case, they used SIGLib for the image encoder. So SIGLib is a new model developed by Google, which builds upon the CLIP model from OpenAI. So SIGLib is trained in a contrastive way on image text pairs, and so you can then only use the image encoder because SIGLib itself actually already consists of an image encoder and a text encoder. But so we're only going to use the image encoder. And then for the large language model, Gemma is a large language model that was released by Google some months ago. And so by basically stitching together these two models along with this projection layer that is then learned during training on image and text data, you get PaliGemma. So I'm gonna start here by running the first few cells which set up our environment. So here I'm installing the Transformers library from source. So by source I mean that I'm installing here from GitHub right away. So it will basically install the main branch here that you can find on GitHub. But of course you could also, because actually there was a recent release which fixed fine-tuning of this new model. So you need to have at least version 4.41.1 available for it to work. And then for loading a dataset, we're going to use the Datasets library, which is also developed by Hugging Face. For training, I'm going to be using PyTorch Lightning. Of course, there are many options here. You could also just train using native PyTorch or using frameworks like Accelerate or the Hugging Face Trainer API. I actually just updated the documentation of this PaliGemma model. So I actually now link if you go to the multi-model models section and you search for PaliGemma, you will find a resources section. So every model page has now also this resources section where you find a link to some useful resources like demo notebooks, blog posts, and so on. And so, yeah, there are actually also notebooks available that leverage the Hugging Face Trainer API. So if you're interested in that, feel free to check them out. The reason I went for PyTorch Lightning in my case is because I want to easily compute metrics on my evaluation set during training. And this is pretty straightforward for now to do with PyTorch Lightning. In the future, we might extend the trainer API as well to support this more easily for multimodal models. Another thing we will be installing here is the PEFT library from Hugging Face. So PEFT is a new library developed by Hugging Face for parameter efficient fine-tuning. I'm going to be explaining later on in the notebook what it actually means, but it basically will allow us to fine-tune the PaliGemma or any other large model on consumer hardware by only training a couple of adapter layers on top of the pre-trained model. And for the quantization, which I also will explain in a bit, we need to install the Accelerate library developed by Hugging Face and Bits and Bytes. And finally, I also will be installing weights and biases for logging, so basically for seeing some metrics during training, like seeing the loss going down or seeing the accuracy going up, for instance. All right, so we have installed all our necessary libraries. Then as a next step, I'm going to be defining some variables that I'm going to be using throughout this notebook. So the repo ID is just a pre-trained model which we are going to fine-tune from. So actually they released like a huge amount of checkpoints on the hub. So there are already 143 PaliGemma models available, and I think if you would search for the Google ones, yeah, there are 118 released by Google, so you can find them in all kinds of different image resolutions. Up till 896 pixels, so this is actually very useful for OCR type of tasks where the model really needs to see the details in the image of a PDF, for instance. And they release them in both the original JAX versions, which is then compatible with their original Big Vision repository, in which they actually released PaliGemma. So this entire library is developed in JAX, which is an alternative to PyTorch. But yeah, we will be using the PyTorch version. So for instance, this is actually the one we will be using in our notebook, has 3 billion parameters. So this comes from the fact that Gemma, the large language model component, has 2 billion parameters, and then the vision encoder has approximately 1 billion trainable parameters, along with the projection layer in between. So that's why we have 3 billion here. You can always also check the size of the model here by going to the files and versions tab. So in this case, we have about 12 gigabytes in size. So that's actually explained by the fact that we have a precision here of 32 bits or 4 bytes per parameter. So 4 times 3 billion is 12 billion bytes, which comes down to 12 gigabytes. And then, yeah, this is the name of the fine-tuned model. So I'm just going to be pushing the model during fine-tuning to the hub as well under my own personal username. Feel free to change this. The maximum length is the amount of tokens that we want the model to learn to generate during training. Of course, this is going to impact the amount of memory that you use. If I would use a smaller value here, yeah, we would require less memory. But I used 512 tokens here for a good trade-off for our particular dataset. And then finally I set some variables here for the weights and biases project to which I will be logging my metrics. So I'm going to be running this cell, and next we can load our dataset from the hub. So a dataset I often use for creating these demo notebooks is this Chord dataset created by the Donut authors. So Donut is another document AI model available in the Transformers library. And so they created this nice data set here where you have the received images as an input with a corresponding ground truth JSON as an output. So that's actually what you need if you want to train such a vision language model. So it's also not the that large, is like 1000 rows, so it's ideal actually for demo purposes. So it's just 2 lines of code to load this from the hub. Of course, now, so Google Colab has this integration with the Hugging Face token, so that's really convenient. So this also allows you to, for instance, automatically push private models to the Hugging Face hub with your token, or load a private dataset from the hub. So this is called Google Colab Secrets. It's pretty handy if you want to link your Hugging Face token with the Google Colab environment. But of course, if you want to create your own custom dataset, I recommend to check out this guide over here in the documentation of Hugging Face datasets, which explains how you can create such a dataset yourself. So particularly these guides here are quite relevant. So basically you need to use this image folder feature here, and then you can specify a path to all your images, and then inside that same folder you need to have this metadata.json lines file, which can have any kind of metadata present for every single image. So in this case it might be this ground truth parsing format. So we can then print out the dataset. So what we get is a dataset dictionary. So this is much like a regular Python dictionary containing various keys. So we have a key for every single split here. So one for training, 800 rows, one for validation, 100 rows, and one for testing. So not that big of a dataset. And then you can actually very easily visualize an example, because if you look here at the features, for instance, of the training split, you can then actually also see what the type is of these individual columns. So the image column is of type image, which means that you can like automatically visualize it in the browser. Here I'm just making it a bit smaller using Pillow, because otherwise it would be quite large. And then the ground truth feature is just a string, but you can actually read it as JSON as follows, and then this is actually the ground truth JSON that the authors of this dataset created. So you can see that it nicely corresponds to the items present on the receipt. And so this is exactly what we want the model to learn to generate given an image. But so note that these models are very flexible. You can make them learn to generate whatever you want given an image and an optional text prompt. So here I'm going from a receipt image to a JSON, but it could of course also go from, let's say, an image of a PDF to Markdown, for instance, or to text right away. This depends a bit on what you want. And actually the authors of PaliGemma are quite creative, because they actually trained it for several capabilities like image captioning. So here you go from an image to a description of that image. You can do visual question answering, where you give it an image together with a certain question, and then the model generates an answer. It can even do object detection, where you can prompt the model with the text prompt, for example, detect cat, and the model will basically output a sequence of tokens representing the bounding box coordinates along with a class label. So that's really nice, of course. This is using some special tokens in the vocabulary of the large language model. And then another task is called referring expression segmentation. So in this case, it again creates these masks. So instead of bounding boxes, in this case it creates masks for these birds, for instance, which is pretty nice. And then for document AI, I think these type of models are super useful. So you can, for example, provide an image of a chart and then ask it certain questions. So it's pretty nice that we can fine-tune them now for these type of use cases. Next, and this is actually something I typically do in all of the notebooks I create, is just creating a regular PyTorch dataset, and then along with that a so-called PyTorch data loader. So you can find the documentation here in the documentation of PyTorch, but basically this is the typical way of how you would create a data set for fine-tuning PyTorch model on. So basically what you need to do is you need to inherit from this class over here, and then I just define it to be custom dataset, could be any name of course, and you need to implement 3 methods for such a dataset. An initializing method that can be anything you want. In this case, I just decided to provide the name of the dataset, the split, and then whether or not to sort the JSON keys inside the ground truth JSONs. Yeah, this is just an additional method that I defined, JSON to token, which we're going to use to convert the ground truth JSONs into token sequences, which the model can learn to generate. But so besides the init method, you also need to implement the length method, which returns the length of your dataset, and the get item method, which returns one single item, one single example of your dataset. So as you can see, it's not that much code. I have actually used or reused some code here from my Donut notebook. So Donut is another document AI model. There are quite a lot of notebooks here, and so I also created a notebook here for fine-tuning Donut on that same dataset. So it's actually inspired by that. And you will find the same kind of JSON to token method in there. However, this notebook is a bit more advanced because we are also adding special tokens to the model before training, like the common JSON keys and so on. But that's something I'm going to skip in this notebook. For simplicity, we're not going to add any special tokens to the model's vocabulary, but oftentimes this may also help in improving the performance even more. So yeah, this init method, what we are going to do here is simply call the load dataset method, which we already called above, but Hugging Face uses caching, which means that if your dataset is already available in your RAM, you don't need to load it anymore. We store the dataset length here in a variable name, which we then return here. And then here, basically, we loop over all the samples in our dataset. We load the ground truth JSONs. Actually, yeah, this could be simplified a bit because some datasets might have like multiple ground truth parsings. That's because sometimes these datasets are annotated by multiple humans, which means that we will have multiple ground truth parsings per image. But in this case, actually, we only have a single one. And then we call the JSON to token methods on each of these ground truth JSONs. So this is actually code I took from the Donut authors, but basically it converts the JSON sequences into token sequences, which the model can learn to generate. So this is straightforward, returning the length of the dataset, and the get item simply takes, based on an index of your dataset, it takes that sample and then it splits it into the image and the ground truth token sequence. Alright, so we can actually now instantiate both the training dataset and the validation set by simply instantiating the class that we defined above and providing the separate splits. This is actually the cell that takes some time. This is probably because it needs to run this JSON to token method on each of the ground truth JSON, so this takes some time. We could actually add, using the TQDM library, we could add a progress bar here so that we can see how fast this is progressing. And then after we create the PyTorch datasets, it's time to create the PyTorch data loaders. So every time in PyTorch you have these two types. So we have the dataset first that defines the individual items or the individual examples of your dataset. And next you need to define the so-called data loaders, which are going to actually provide batches of data based on the dataset. And so why do we need batches? Well, that's actually because neural networks like Gemma, PaliGemma, and so on, they're not trained on like every image and ground truth JSON one by one. We typically feed batches of data to the model because these models are optimized using optimizers like Adam and AdamW, which is a popular optimizer for neural networks. And so we need to feed batches of data through them. And so that's what these data loaders will do. So a data loader in PyTorch is basically going to take samples, items of your PyTorch datasets, and is going to batch them together. And the way they are batched together, you can define that yourself by implementing a so-called collate function. So collate functions just define how you want to batch together examples, individual items of your dataset. And it's for that we're going to use this processor class. So in Hugging Face transformers, we will typically, in the documentation of these multi-model models, we already support quite a bit of them, as you can see right here. You will typically find not only the model, so in this case the PaliGemma for conditional generation, which is the model we're going to be fine-tuning, but also the pre-processing class, which in this case is called PaliGemma processor, which can be seen as a wrapper on top of an image processor and a tokenizer, because yeah, this is a multi-model model, so we need to basically prepare both the images using the image processor and the text using the tokenizer for the model. And so the processor class is actually going to be a wrapper on top of those, and it's going to allow us to prepare the data for the model. So yeah, here we're going to actually use this processor class, as you can see, and I'm defining a separate collate function for training versus evaluation. The reason for that is because during training, we need to also provide the labels to the model besides the inputs. So the inputs to the model will consist of the image prepared in the format of the model. So in Hugging Face transformers, if we prepare an image for a model, we typically then call them pixel values. So this is typically a resized and normalized version, and also a rescaled version of the original image. And then the text inputs are these three here, the input IDs, the token type IDs, and the attention mask. If you don't know what these mean, I would recommend to check out the guide on what are input IDs. I think we have documentation on that in the glossary. And this is actually also nicely explained in this video. But it's basically the way we represent text for a transform-based model, along with the token type IDs and the attention mask. So these are the text inputs. This is the image input prepared for a model. And then the labels, this is actually the targets that we want the model to learn to generate. So basically here what I'm doing is we take a list of individual items that we get from our PyTorch datasets. So as we saw above, the getItem method returns a tuple, which also means that here we're going to get a list of tuples of the individual items. So then we create this images list over here by taking the first item of each of these tuples, and then the labels are the second item of each of these tuples. And for the text input, I created a custom text prompt over here, which I just called extract JSON. So basically, this model is going to get the received image along with the text prompt extract JSON as an input, and then it's trained to produce the JSON as an output. So then we feed all of that to the processor class. We can feed the labels using this suffix keyword argument. We specify that we want PyTorch tensors to be returned because the model which we're going to be training is all in PyTorch. So that's why we need to specify here the PT flag. And then, so as I said in the beginning of my notebook, I use a maximum length, which is the amount of tokens that we want the model to generate. And in order to batch these different JSONs together, we need to make sure that they are all of the same exact length, that they all need to have the same amount of tokens. So that's why we do this padding and truncation over here. So padding means adding zeros basically, or the special padding token to the text sequences so that they are all of the same length for those that are not long enough. And then for texts which are too long, we are going to truncate them, which is why we feed the truncation argument over here. But there's actually a nice guide regarding padding and truncation in the documentation as well, because there are several ways to do padding and truncation. Like in this case, we only want to truncate the second sequence, which means the text prompt. We're not gonna truncate the first sequence. And then, this is a special flag. To be honest, I don't know whether this flag is now required anymore. I just copied this from the other notebook that you can find in the documentation of PaliGemma. And then it's going to create all these inputs. So this is actually going to return a dictionary. The reason I'm simply taking each of the keys here from that dictionary and returning them as a tuple is because PyTorch Lightning had some difficulties with processing dictionaries for some reason. So that's why I convert our dictionary here to a tuple. And then for evaluation, it looks a bit different because then we actually don't need to prepare labels for the model. So as you can see right here, I only feed the text prompt and the received images to the processor, so it's not going to create the labels. But I do provide the ground truth answers, so the ground truth JSON sequences. As an additional output here of the collate function, because this is going to be useful for us in order to compare the predicted JSON sequences of the model to the ground truth answers over here, because this will allow us to compute metrics, as we will see further. And then creating these PyTorch data loaders, for that you just need to inherit from this class over here. So from torch.utils.data import data loader, very similar to how we created a PyTorch dataset. You can then specify your dataset to that data loader, and it's gonna, based on the batch size that you provide, so it's gonna then batch together these examples, and the way they are batched together is defined by your collate function. And so typically during training we also specify the shuffle equals true flag, which means that it's going to shuffle these examples over dataset in order to have like a random, we will always have like 2 random received images along with their JSON sequences. And then you can check out the first batch by iterating over that data loader, because this is actually going to return a so-called Python generator over which you can iterate. So what I typically do is like taking the first batch of that data loader and then simply seeing what we get, because it's very important, of course, to make sure that the inputs that we feed to the model are correct, because this is actually something I learned from a really nice blog post by Andrej Karpathy, a recipe for training neural networks. Which has a lot of tips and tricks regarding debugging your training runs of neural networks. And actually one of the most important things he says is like, make sure to check your data, like the data right before it gets fed to the neural network. And in this case, this is exactly the data that comes from our PyTorch data loaders. The input IDs, these will actually be just like, as you can see, integer numbers representing tokens in the vocabulary of the PaliGemma model, and we can convert them back into text using the batch decode method. So this is actually what the model will get as an input. So as you can see, it's like a long list of special image tokens, and then we have the special beginning of sequence token, then we have our text prompt, and then we have the ground truth JSON. So actually, maybe let me explain this quickly in Excalidraw. The way these models are trained. So let's say this is our PaliGemma model, which is a transformer based model. So we are going to feed the input IDs, the attention mask, along with the token type IDs to the model. And so the input IDs, they can look like this. So I'm just gonna a long sequence of these image tokens. Then we have our beginning of sequence token, then we have the extract JSON prompt, and then after that we have our ground truth JSON sequence. So I'm just gonna copy over here the first few of those. Alright, and maybe let me make it a bit bigger, like so. And then the attention mask itself is actually just a tensor containing like to which tokens the model should pay attention versus not. So in this case they are actually all set to 1, which means that all of the tokens will be involved in the attention computation. So So there are going to be 1 for all of those tokens. But yeah, sometimes you want the model to ignore some tokens, which is why we then set them to 0. And then the token type IDs, let me check them out as well. So in this case, yeah, I'm actually only taking a look at the first one of the batch of 2. So in this case, we actually, as you can see, we indicate, I think, which tokens are image tokens by 0. And then which tokens are text tokens. This way, the model can learn like separate embeddings for those. So this is actually what we're gonna feed to the model as an input. But so yeah, keep in mind, like I'm representing these here with text, but actually the thing that the model will see as an input are just these numbers, these input IDs. So yeah, so actually what the model will see as an input here is this, followed by another integer representation of that token. And then followed again by, and then we have the beginning of sequence token, so that's then the token with ID 2. And so on. And then, yeah, let me just copy over these as well. And so on. So this is actually what the model will see as an input. So let me maybe put these in red, because these are like the actual inputs. Well, not these string representations, rather these numbers over here. Yeah, I'm afraid that if I put something here in red, it's going to turn everything in red, so let me skip that. But so we basically feed these numbers here along with the attention mask and the token type IDs through the model, and what the model is basically going to do is it's going to compute an embedding for each of those tokens in parallel using the attention mechanism. So yeah, this is actually done for all of those tokens. So we have, like, we will have 512 tokens because we decided to pad them and truncate them all to the same length. But so yeah, it's important to know that transformers, they do things in parallel, which means that yeah, they're going to compute an embedding vector for each of those tokens. And then let's take a look at the labels, because those are like the targets of the model. So as you can see, they look as follows. So they start with a lot of -100, -100, -100, and so on. So why is that? Well, actually, for every of these tokens, the model is going to predict like which token should come next. So basically, we want the model to learn that after this token over here is total, for instance, we want it to predict its total price, and then after its total price, we want it to predict 50,000, which is then the actual price, and so on. So the model is going to be trained to predict the next token. But so the labels over here are going to look like this. So we'll have -100, -100, and so on. This is because we don't want image tokens to be involved in the loss computation. So if you go to the cross entropy loss, which is the loss function used by models like PaliGemma or any other large language model which is trained to predict the next token, you will see that the ignore index here is set to -100 by default, which means that if we set labels to -100, these are not involved in the loss computation. So the model is not penalized for predicting the next token for these. However, then after that, after these image tokens, as you can see right here, basically after the token 2, we're gonna have this as the label, and then after this, the model will be trained to predict this token, and so on. And then basically here the model is going to predict some token, like here it's going to predict 6, for example, token with ID 6, but as the label is -100, we're not going to incur any loss. But then actually here between the predictions, and the labels, we're gonna compute the cross entropy loss. And of course, yeah, there's some way here to go from this embedding here that the model computes for every single token to that actual prediction. That actually happens using a so-called language modeling head, which I actually have a different video about. But yeah, basically it comes down to the model will predict like a token ID here for every single token in the sequence that it thinks comes next after the other token. And so it does this in parallel for each of the tokens, so that we can also compute the cross entropy loss in parallel. So I'm just gonna type here some random numbers, but this way we can compute the cross entropy loss between each of the tokens in parallel. And so this is actually how each of these transformer based models like PaliGemma, but actually Llama, ChatGPT, any kind of transformer based model is actually trained in this way. So yeah, but yeah, another thing to add here is that these labels, when users create them, they are typically just a copy of the input IDs with then special tokens like image being replaced by -100. But we then also need to shift the labels one position to the left so that the model always is trained to predict the next token. But this shifting itself actually happens inside the transformers library. So if you go to the PaliGemma model implementation and you search for the cross entropy loss, you will see here that the labels get shifted one position to the left in order to make sure that the model predicts or is trained to predict the next token. Alright, so yeah, users typically just create labels as a copy of the input IDs, but with special tokens replaced by -100. Alright, but I think we've already explained quite a bit here how these models are trained. And so this is actually also like why I always check the inputs before I feed the model, before I feed them to the model. Like here I also check for instance the labels, so they're just a copy actually of the input IDs, and then the shifting itself one position to the left happens internally in the model, so this all looks fine. So actually you can also see here what the model will get as an input and what the model is is required to predict. So let me just show them for all the input IDs here and all the labels. So as you can see right here in the very beginning, yeah, we feed these tokens as an input and the labels for them are all -100, -100, so the model is not trained for those. But then after some time, as you can see, okay, so apparently token with ID 2 is also a special token. So the label here will also be set to -100. But then, yeah, here we actually start. And so as you can see right here, the labels are just a copy of the input IDs. But so internally the model will shift this one position to the left, which means that this becomes the label for this input ID and this becomes the label of this input ID and so on. Right, and then we can actually check the same for the validation data loader. So there we actually only feed the prompt to the model, so we don't actually have the ground truth JSONs here in the input IDs, because we're only going to feed this prompt to the model. So basically it's only going to see up till here, extract JSON, and then here we're going to take the prediction, like the next token that the model predicts, and then we're going to feed that additionally to the model, and again we run the forward pass in a loop. So this is called autoregressive generation, but I do have a separate video on that if you want to check it out. Alright, so once we have defined the PyTorch datasets for training and evaluation, and we have defined the corresponding PyTorch data loaders, it's time to train a model. And so for training a model in PyTorch, there are very different frameworks which you could use. One popular class that a lot of people use is the Hugging Face Trainer API. So it provides an API to train models specifically optimized actually for models in the Hugging Face Transformers library. Alternatives include Hugging Face Accelerate, which is a separate library developed by Hugging Face for people that want to implement their own PyTorch training runs, and Accelerate then actually takes care of making sure that the model runs on a multi-GPU environment and so on. So as you can see, it only requires very few lines of code to be changed. And then a third option I would say is PyTorch Lightning, which I'm going to be using in this notebook. And so in PyTorch Lightning, you need to define a so-called Lightning module, which basically is going to organize your PyTorch code into a few sections, and it's going to take care of a lot of things for us, which we often call the boilerplate. So things that we often need to redefine for every single training run, things like device placements, like making sure that the model is put on the GPU, making sure that our data is put on the GPU. It's going to take care of the backward pass, making sure that the model is put in the right mode, training versus evaluation, and so on. It also supports things like gradient accumulation, gradient checkpointing, all these kind of things that are going to help us in training a model in PyTorch very easily. So you basically need to inherit from that class the PyTorch Lightning module. And then you can implement these various methods, like how does a training step needs to look like, how does a validation step needs to look like, which optimizer do you want to use, and then here I'm specifying my data loaders. So as you can see, it's quite minimal. And so the important thing I add here, is this distinction here between the training step and the validation step. So the training step, as you can see, we feed the input IDs, the attention mask, and the token type IDs, as well as the pixel values. So that's actually something I didn't include here, but actually besides that, we also feed the pixel values, which is a PyTorch tensor of shape, batch size, number of channels, height, width. We also feed that to the model besides the text inputs, and then the labels are going to be used to compute the loss. So here we feed the labels as well, and the model is going to calculate the cross entropy loss for each of the tokens in parallel, and it's going to return that. And then PyTorch Lightning is going to call the loss.backwards, which then computes the gradients of the parameters with respect to the loss. And then here we have the validation step. So this looks a bit different. So as you can see, for inference, we use the generate method. So in that case, we don't just forward the inputs through the model, as you can see right here. We don't call the model, but rather we call the generate method, which is going to do this autoregressive generation. So this is actually how training looks like, where we compute the cross entropy loss. Compute cross entropy loss in parallel for all tokens. But then, inference looks different. Sorry. So let me just copy over this figure. Because in that case, we will still feed the pixel values, the input IDs, the attention mask, and the token type IDs to the model, but it's gonna, only feed the prompt. We are only gonna feed the prompt to the model. And then, because the model has been trained to predict the next token. Oh, sorry, I'm messing up here with this one. So since the model has been trained on predicting the next token, we're not going to compute a cross entropy loss here. The model is basically going to predict a next token for each of the tokens. So that's actually a bit funny. Like even at inference time, the model is going to. So inference is also called autoregressive generation for large language models. So we get a prediction actually out for each of the tokens, but of course we're only interested in like what the model is going to predict here after this JSON token. So then it might predict like the token with ID 85,000, let's say. Well, typically these vocabulary sizes are not as large. Let's say the token with ID 5,931. So then we can convert that back into some sort of text, and then it might like predict this start of total token. So this is what step 1 looks like in autoregressive generation, and then this process basically repeats. So then we basically are going to feed this. So this would be step 1, and then as a second step we're gonna do the exact same thing, but we're gonna take the prediction of the model, we're gonna feed that here as an additional input to the model, and then the model is again gonna predict a prediction or make a prediction for every single token in the sequence in parallel. We're interested only here in what the model is predicting after that token, might be this one, and then we can convert that back into text. So yeah, this string representation here might be, and then here it might predict like an actual total price, like 38,000 euros, for instance, let's say, and so on. And so this is actually how autoregressive generation works. So it works in these steps. So this is step 1, where we feed the prompt, only the prompt to the model along with the image. The model makes a prediction for the next token, and then we take the model prediction, add it back to the prompt, and we repeat the process. And this happens until the model predicts the so-called end of sequence token, which is a special token in the vocabulary of the model. I think you can also find this if you go to the PaliGemma model and you check the vocabulary. There is some kind of end of sequence token. Yeah, this one. So this is a special token in the vocabulary of the model, and if the model predicts that, then we know that the model wants to stop generation. And so this is the big difference, I would say, between training, where you compute across entropy loss in parallel across all your tokens, whereas at inference time we do this autoregressive generation step where we have forward passes for each step of the generation process. And so that's what's happening when you call the generate method. And so here I'm specifying the max new tokens argument, which is basically gonna define like how many times you want to repeat this process at most. So we're gonna do that at most 512 times. But so there are quite a bit of tricks involved in like making this autoregressive generation go as fast as possible with things like key value caching. I recommend to check that out if you want to know like how people can like speed up autoregressive generation with transformer-based models, but that would require a separate video. And so then we basically get these generated token IDs back from the model, and then we can turn them back into text using the batch decode method of the processor, and we're gonna chop off our prompt. We don't need the prompt anymore. And then, so we basically have our predicted sequences that the model has predicted, and we can compare them against our ground truth answers that we included in our validation data loaders. And then here I'm computing the so-called Levenstein edit distance. Yes, something like this. So what is doing is basically computing how many edits we would need to make to the predicted sequence in order to get the ground truth sequence. And so the fewer edits we would need to make, the better, of course. And so the edit distance is like a formalized metric for this, which is gonna allow us to track the performance over time on our validation set. So this is all also taken from the original Donut repository, which is a model that I contributed to the Hugging Face Transformers library 2 years ago, and it's still a very nice end-to-end transformer encoder-decoder model for document AI. But yeah, PaliGemma is only the decoder part of the transformer. So here then I'm specifying which optimizer to use. I'm just going to be using the AdamW optimizer here, which is a popular one for fine-tuning transformer-based models. And here I'm specifying the data loaders. All right. Now, there are actually a couple of ways to load or pre-train model from the hub and then start training it. So what we used to do a lot of times was so-called full fine-tuning. So by full fine-tuning, we mean we take this 3 billion parameter model and we're going to update all of the weights during our fine-tuning process. So this is known as full fine-tuning. However, with these larger and larger models that we have nowadays, this becomes quite expensive in terms of memory usage. For instance, if you train with an optimizer like AdamW, we typically use mixed precision during training. So what we mean by that is that we typically store the weights of the model. So that's the precision. You can actually see that if you go here to the model, you can always see the precision on the right side. So here in this case it's 32, floating point 32, which means 32 bits or 4 bytes are used per parameter. So that's another thing I could explain right here. The precision in which models are trained and stored. So if you use 32 bits, if you remember from high school, then 32 bits means 4 bytes because a single byte is 8 bits. So for our PaliGemma model, we have 3 billion parameters. So if we would require 4 bytes per parameter to store them, that requires 12 billion bytes, or also known as 12 gigabytes. So that explains actually why if you see the files and versions tab, you have about 12 gigabytes in total size for your model. So this is also known as full precision. But nowadays we also have half precision, which is only using 16 bits or 2 bytes per parameter. So this means for our model, 4 billion parameters times 2 bytes per parameter. So this would be 6 billion bytes or 6 gigabytes, which is already quite okay. And so during training, one typically uses something called mixed precision. So mixed precision basically means that we're going to store the weights of our model in half precision, so in 16 bits. So store the model parameters in 16 bits or half precision, but store the optimizer states in 32 bits. Because those optimizers, like AdamW, they typically also require quite a bit of memory during training, because they also store some so-called optimizer states, like second order derivatives and things like that during training. And so those typically require quite high precision, because otherwise the model starts to diverge and the model is not training well. So mixed precision is like some kind of best of both worlds, where we can store the parameters of the model in 16 bits, but then store the optimizer states in 32 bits. I think this is also explained in the documentation. There's actually a very nice guide on methods and tools for efficient training on a single GPU, which explains this mixed precision technique. So yeah, this is all explained right here. But so a thing I also learned is that if you train a model with an optimizer like AdamW in mixed precision, then the amount of memory required during training is about the number of parameters times 18. If you train a model with AdamW during training with mixed precision, you need to multiply the number of parameters times 18. So in our case, we have 3 billion parameters, and if you multiply that by 18, that's 54 gigabytes of GPU RAM required. So that's like, a trick I learned, and that is actually also explained, I think, in this guide. So it would mean that we would require 54 gigabytes of GPU RAM to do full fine-tuning using mixed precision, which is of course quite a bit, because we are training here on an L4 NVIDIA GPU. So NVIDIA L4 GPU memory is 24 gigabytes. So that would not fit into our GPU. So we cannot do full fine-tuning of PaliGemma. However, luckily there are some newer methods being developed, and which are now nicely supported by Hugging Face libraries called LoRa and QLoRA, which are basically going to allow us to train these giant models even on consumer hardware like an NVIDIA GPU with only 16 or 25 gigabytes of RAM. LoRa itself is a method developed by Microsoft It stands for low rank adaptation. And the whole idea of LoRA is basically to freeze the weights of our pre-trained model. So we're not going to touch or change anything to the weights of our pre-trained 3 billion PaliGemma model. We're only going to add a few adapters on top of those, a few like linear layers. We're going to only train those. And this technique is known as LoRA and basically allows people to train models in a much more parameter efficient way, which is what PEFT stands for, parameter efficient fine-tuning. So I think there are also definitely some nice guides on that, but the main idea is basically that we're not going to touch the pre-trained weights, so we're going to freeze them, keep them untouched. We're going to only add adapters on top of those, so-called adapters, here shown in orange, and we're going to only train those. So this is another way of nicely showing it. So yeah, we're going to freeze or not train the pre-trained weights, but only add those adapters on top, which is going to greatly reduce the amount of memory required. And so this is offered in a separate PEFT library by Hugging Face. And then another thing which is going to even further decrease the amount of memory required for training this model is the QLoRA method, which is the idea of combining LoRA with quantization. So by quantization, well, actually, this is already a form of quantization, because here we go from 32 bits to 16 bits, but you could go even lower. So there's also int 8 nowadays, so this means 8 bits or just a single byte to store every single parameter. So if we have 3 billion parameters times just a single byte per parameter, that would mean that we only require 3 gigabytes to load our model. And nowadays you even have int 4 or even 2 bits or 1 bit. But let's, like in my notebook, I'm going to be using 4 bits, so only half a byte, which means that we only will require 1.5 gigabytes to load the PaliGemma model into our notebook. And so QLoRA, which is greatly explained in this blog post over here, is just the idea of combining LoRA with quantization. So basically, it would mean that if this is our pre-trained PaliGemma model, yeah, we're gonna freeze this. So I'm gonna put it in blue. We're gonna not touch upon that. We're just gonna add some adapters on top. Okay, I want to, yeah. Let me just call them adapters. So red is what we're gonna train and blue is what's gonna stay fixed. And so we're gonna quantize this. Quantized in 4 bits, which means that we're only gonna require 1.5 gigabytes for loading this pre-trained model and then freezing it. And those adapters are then typically well trained in float 16, so in half precision or 16 bits. But as we only have a few adapters, this is gonna be no problem for us. So this whole idea is known as QLoRA. And this is actually what I'm going to be using here. So if you would do full fine-tuning, this is how you would load the pre-trained model from the Hugging Face hub. So you just call the from pre-trained method on the class. And yeah, typically we don't actually need to fine-tune all of the models, all of the parameters. We typically freeze, in this case, the vision encoder as well as this projection layer, and we're only going to update the large language model. Of course, you could also remove this and just do full fine-tuning. It's a bit of up to experimentation what gives the best results. But in our case, we're going to be using QLoRA. So this is why we need to define this bits and bytes configuration. So this basically is going to define how we're going to quantize or shrink down the size of our model to only 4 bits with some clever algorithms. So in the Hugging Face Transformers library, there are a lot of quantization methods already available, like AWQ, GPTQ, and bits and bytes, which is the one we will be using. So these are all like clever algorithms which come up with clever ways of shrinking down the size of our parameters to fewer amount of bits while keeping the performance mostly the same. So this basically will define how we quantize, so how we're gonna quantize this into 4 bits. And then here the LoRa configuration then defines where we want to add these adapters on top. So that is defined using the LoRa config. This is a hyperparameter regarding LoRa called the rank. I just used a good default value here, and then the target modules is basically defining where we need to add these adapters on top. And so we typically add them on top of the query projection, the output projection, the key projection, the value projection layers of the attention layers of the model. But this is actually pretty low level, because then you would need to go to the actual implementation of a model like Gemma or PaliGemma, and then you can find where certain layers are defined. And so it's actually there that we're gonna add these adapters on top of those. And this is known to produce good results. And then you need to wrap your model in this get path model. Okay, I need to first run this cell. There might be an issue here with my Hugging Face token. It says that it's gated, but I have access. So let me just restart the runtime and run before. But this way, yeah, we basically will see that we are only gonna require 11 million parameters to be trained. So those are the adapters here. So only 11 million trainable parameters. And then the total amount of parameters is actually about 3 billion. So we will have here roughly 3 billion untrainable, also called freezed parameters. Sorry, freezed is horrible English. I should say frozen. Sorry for that. Okay, so once we have defined all of that, it's basically just a matter of instantiating the PyTorch Lightning module. And then, yeah, here I'm actually storing some hyperparameters regarding training in a Python dictionary, such as the number of epochs, whether we want to check the validation metrics every so many epochs, whether we want to use gradient accumulation, which is another trick to train models on consumer hardware, the batch size we will be using, because those are then referred to in the Lightning module. So here I'm instantiating the Lightning module with our configuration, and then I provide things like the learning rates, the batch size, and so on to it. So in this way we can store all these hyperparameters in this dictionary. And then another thing I do is defining the callbacks, so-called callbacks. So these are arbitrary Python programs that we can run during our training. So here we'll be using 2 callbacks, which one is provided by PyTorch Lightning by default. It's called early stopping. So early stopping means that we're gonna stop the training once the performance metric, so the evaluation metric on our validation step, or on our validation set, stops improving after a certain amount of epochs. So in this case, we say that we want to stop training if the validation edit distance, this Levenstein edit distance, stops improving after 3 epochs. And we need to specify that we want to minimize this metric. And then here I also define a so-called push to hub callback, which is going to push our model to the hub during training, so after every epoch as well as at the end of training. This is of course something you can customize. But so yeah, you could also of course also push your model as a private one, so it's such that not everyone in the world can see your model. Alright, so then it's time to train our model. So here, yeah, actually I'm providing some hyperparameters regarding training, like the max number of epochs and so on, to the trainer. It's also here that you can pass the weights and biases logger in order to track progress of your training. However, I noticed there was an issue in Google Colab when providing the weights and biases logger to the PyTorch Lightning trainer. So we won't be doing that, but yeah, PyTorch Lightning takes care of automatically making sure that your model training runs on one or multiple GPUs or other types of hardware. And then here we provide things like gradient clipping, gradient accumulation, and other techniques that can be used to optimize the training run. So here actually we are specifying that we are training with mixed precision. So this is actually the thing I explained earlier in this part over here. So we're gonna train these adapters using mixed precision. So the optimizer states will still be in float 32 in 32 bits, but the adapters themselves will be loaded in 16 bits. And then you can see some logs over here. So we'll see that we only have about 11 million trainable parameters. And then yeah, the training is actually progressing. So as you can see, it estimates that the training itself for a single epoch takes about 4 minutes. We are using currently a batch size of 2. This is also, of course, because I limited this because we're running this in Google Colab. Of course, feel free to change the batch size if your hardware allows it to do so. And so also feel free to play around with models with a higher image resolution and setting the maximum sequence length for the text tokens can also be tweaked depending on your use case. In our case, we're using 512 tokens. Okay, but yeah, this training, I'm just gonna let it run actually until we see the first evaluation, because this will allow us to see the logs, which I can actually already show maybe in the meantime by going to my Transformers tutorials repository, where you can also find my PaliGemma notebook. And there I can show you how the logs look like during the fine-tuning run. So they look like this. So as you can see, you get like the predicted sequences together with the ground truth sequences, and then the normalized edit distance is computed, and so you can then track the performance over time. Of course, you can also turn off this flag if you don't want to print these during training. This can be set using the verbose flag, I think. Yes, there's this verbose argument that I added to the configuration, and then depending on whether it's set to true or false, this gets printed. Alright, so we're halfway there, so I'm just gonna speed up the video a bit until we are at the end of training. Alright, so we have arrived at the validation step, the first validation step. So of course you can actually tweak this using this check val every n epoch argument, which is currently set to 1, which means that after every epoch we are going to run evaluation on our validation set. And so then you will see these logs being printed. So now we are at an edit distance of about 0.3 for this first example. And so of course the goal will be to go to 0, to an edit distance of 0. Alright, so that's for training. And so also after this validation step is being run, the model is going to be pushed for the first time to the hub. So this is because of the push to hub callback that we defined earlier, which will be running after the training epoch as well as the validation step. So as you can see, there are still some reading mistakes. Here it's mistakenly predicting a total price of 100,000, whereas it should be 20,000. This could have to do, of course, with the fact that it has only been trained for a single epoch right now. So there's still a lot of work there. But it looks like we are on the right track. Okay, so now as you can see, it's pushing the adapters to the hub. So now if you go to the Hugging Face hub, you will see that it has created this repository, and in the files and versions tab you can see that only these adapters are being pushed to the Hugging Face hub. So this is a file of only about 45 megabytes. So this is of course very small compared to the large model, which is about 3 gigabytes in size. And then, yeah, the second epoch is going to be run, but I'm going to be pausing the training here for just showing you also how inference can be performed. So at inference time, yeah, we are going to be using this generate method, which implements the autoregressive generation. So in every for pass, we predict one token, which we append to the input, and then we predict the next token and so on. So for that, I'm going to be using the test set. So this is on an image which the model definitely has not seen during training. It's also not used during validation because that was the validation set. So that's actually the difference between a validation set and a test set. The test set is like not seen at all during training, whereas a validation set can be used for things like early stopping, which means stopping the training when performance on the validation step, on the validation set stops improving. And then, yeah, there's this PEFT integration in the transformers library. So if we provide our fine-tuned model ID right here, like this one, it's going to automatically load the adapters along with the so-called base model. So the base model is actually the blue thing over here. So it's going to load both at the same time. The reason it can do this is because if you check here the configuration of our adapters, there is a base model name or path. So here we know that this adapter has been pre-trained on top of the PaliGemma model from Google. And so then, yeah, we provide the inputs to the model. So in this case, as you can see, it doesn't seem like there are any token type IDs being created. At inference time, we only feed the text prompt along with the image to the model. And then, yeah, using the generate method, we get some generated token IDs back. And then here I'm just removing the prompt from those generated token IDs, and we can convert them back into text using the batch decode method. So yeah, currently it's actually autoregressively generating text. Actually, I noticed right now that I'm not leveraging the GPU. So this was done on a CPU, because actually you should add here model.to CUDA, for instance, if you want to run the inference on a GPU. But as you can see, it was also quite fine on the CPU. So this is also because of the fact that the model is not too big, so it can probably also be run on the CPU. And then here I use the token to JSON method, which you can also find in my transformers tutorials repo. I took this from the Donut repository. So Donut is this other document AI model, and there I defined also this token to JSON method, which is pretty handy if you want to convert the token sequence back into an actual JSON object. So if we do that right here, then we actually get our predicted JSON out. And of course, this is only going to improve if we train the model for more epochs, because I actually trained it for just a few. So notice also that I haven't done any hyperparameter optimization yet, like number of epochs, learning rate, the rank of the adapters when using LoRa, gradient accumulation, and so on. I would say, yeah, play around with these, because there hasn't been any hyperparameter search being done or optimization being done yet. I mainly create these notebooks for tutorial purposes. So this is just a disclaimer that I wanted to add. All right, so yeah, that actually concludes my video on PaliGemma fine-tuning. I hope you learned something about fine-tuning open source transformer-based models such as PaliGemma. Of course, every week nowadays there's a new model coming out, so be sure to also check out other models available in the Hugging Face Transformers library. PaliGemma is only one of the many that we support. A nice proxy is also looking at some of the current trending models, like currently the Phi 3 vision model by Microsoft is also one of the newer trending small vision language models. So yeah, keep that in mind. Alright, so that was it. I hope you enjoyed my video, and I see you in the next one. Bye bye.